I will talk today about a class of non-commutative spacetimes together with their deformed Poincaré quantum group of symmetries. The talk is based on these papers mainly, and there's also stuff from less recent papers with Giuseppe Fabiano and Fedele Lizzi. All right, the general framework or my interest, it is to study quantum homogeneous spacetimes, so non-commutative spacetimes that admit a group of isometries. It will be a deformation of the Poincaré group. I'm putting the focus here on this invariance and whether we can preserve this Poincaré invariance, even though in a non-commutative deformed sense, all the way in our construction of physical theories. What do I understand as Poincaré invariance when I have coordinates that do not commute, like here? Well, in another inertial frame, whose coordinates will be indicated with x prime, the same commutation relations will hold for the new coordinates, okay? So all the observations that you can make that regard the non-commutativity of your space-time in one reference frame will give the same answers. This implies that this fu mu nu non-commutator object is not a tensor, okay? It's although it has indices mu and nu, we shouldn't let it rotate when we perform a Lorentz transformation or a general Poincaré transformation. I will show specifically how this can be implemented. If this holds, an f will probably depend on some length scales. Okay, it could be just quadratic in x, but I will specifically avoid these examples because I'm interested in Lie algebra type non-commutativity. So if it depends on some length scales and I can somehow detect these length scales with measurements in a local reference frame, inertial reference frame, these measurements will give the same answer in any reference frame. So this length scale or length scales will be relativistic invariant, just like the speed of light. I'm interested in this because for decades I've been interested in trying to find a consistent physical or model that embodies this old idea by Amelino Camelia in the early 2000s of doubly special relativity, or having a second relativistic scale, which is a length or an energy scale, and it's the same for all observers, okay? Now, this is the general setup. It's pretty much the same mathematics that Maria showed just before, but I like to describe it in terms of the algebra of functions on the group. So to work with finite translations and finite Lorentz transformations, it's all equivalent in the Lie algebra setting. It's just a dual description, okay? All right, standard Poincaré, commutative normal Poincaré group is described as an algebra of functions. It's a commutative algebra of functions because the product is this, is the point-wise product between commutative functions, okay? The coordinates are particular functions on the group, and it's convenient in the case of the Poincaré group to use the finite translation A and lambda, the Lorentz transformation. Lambdas are constrained because otherwise they would be general GL4 matrices. So they satisfy the constraint that they preserve the metric. Okay, they're Lorentzian orthogonal matrices. The metric is a standard Minkowski metric. The group structure, the Lie group structure, is encoded in this dual picture in which I'm working with functions, not with the group itself, by a co-algebra, by a co-product, sorry, that encodes the group product, okay? So these two give me their product. If I apply this on elements of the group, I get how I can compose 2 points on the group, okay? The co-unit gives me the coordinates of the identity of the group, and the antipode gives me how to build the inverse given the coordinates on the group, okay? Finally, I can define a homogeneous space for this group as a comodule algebra. I'll call it M, it's Minkowski space in this commutative case. And it's a comodule because there is this coaction that goes from X to the Poincaré transformed coordinate X, okay? So this is a convoluted way to describe a commutative standard Poincaré group, but it has the advantage that it generalizes to the non-commutative case, where I relax this rule that these rules that the coordinates commute with each other. So I will be interested in generalizing a set of non-commutative spacetimes, and in particular non-commutative Poincaré groups, that, first of all, they have in common that they are all named after Greek letters for historical reasons. And I would like to preserve this tradition, okay? So, second, they have a lot more in common. The algebraic properties, the constraints on the Lorentz matrices are the same. The Lorentz matrices all commute in all of these three models. There are not three, actually, there are several. And the coalgebra is the same because the Lie group structure is the same. I compose Lorentz matrices in the same way, and I compose them with translations in the same way. All that changes is the commutators between translations and between translations and Lorentz matrices. Yes, I can just do that. These are the commutators for two translation coordinates in the three models, and these are the commutators of translations with Lorentz matrices. The first is Moyal, very well known, studied for decades in all possible ways. And the theta is the Greek letter associated to Moyal. The theta Poincaré group has only, its only non-commuting part is the translations, and they close this algebra with the Lorentz matrices. Then there's kappa, which usually when we say kappa without specifiers, we refer to the time-like version. There are three according to this guy here, this is not a vector again, it doesn't rotate, but it's four real numbers that parameterize the models. Whether this thing is, if we calculate the Lorentzian norm of this thing, whether it's positive, negative, or zero, it gives me three different models that are inequivalent under automorphisms of the Poincaré group. That this is the sense in which they are separate models. And so in this case, I have also commutators between translations and Lorentz matrices that depend only on the Lorentz matrices. Finally, there is what I call zeta, because originally Lukierski used the Greek letter zeta to parameterize the models. Again, it's something that depends on whether zeta is lightlike, time-like, or space-like, so there's three models. The time-like model is what we call r-Minkowski that Maria described. The space-like model is usually referred to in some papers as lambda Minkowski, and that lightlike is free for the catch. You can decide your letter. It doesn't have an assigned letter. So in terms of this quote-unquote vector zeta, these are the commutation relations of the A's and lambdas, and the commutation relations between A and lambdas. Everything is a star algebra. The involution is pretty much straightforward. Everything is covariant under this involution. Okay, so this is a few references for the various models. I just leave it here without further comments. This is for the Poincaré groups. Don't get mad if I put a reference from 2009 for theta, because this is the first time that the group A and lambda in those coordinates it was expressed, okay? The comodules, the non-commutative spacetimes that are invariant or covariant under these groups are obviously theta, kappa, and zeta Minkowski, okay? And this is them. They are all closed Lie algebra, although this is really a central element, so it can just be identified with the identity, with the unity. And they're all covariant under an undeformed coaction. So the Poincaré transformation of coordinates is just a standard one, okay? So they have some nice common features, these spacetimes and their quantum groups. These are some references. Theta is very old, since Moyal and Grunwald talked about that in these terms as a non-commutative space, but then in string theory got discussed again for other reasons. But the form Poincaré group wasn't introduced until, wasn't relevant for the string community until discussed in the context of ADS-CFT, as Richard said, I think. Okay, so these are the first times that the other two non-commutative spacetimes appeared. All right, again, let me discuss quickly the meaning of the covariance of these things. The comodule, I already said it in the introduction. I have the comodule property, which means that this transformation, if I calculate the commutators and use the commutation relations of the quantum group, for example, in the case of theta, these guys will cancel these guys and will give me again a theta, okay? So in a different reference frame, if I have, for example, uncertainty relations between two coordinates that have to be preserved because of the commutator, the same uncertainty relations, not the ones with rotated or boosted theta, will hold. This is my idea of Lorentz invariance here, okay? All right. Another concept that is not discussed often, but I think is important to do field theory, is the fact that to do physics, we can't work with one point. We need to have what I call multi-local functions, so functions of more than 1 point, all right? And point functions in QFT, right? How do you algebraize this concept? Well, with the tensor product of the algebra of functions, no? Problem is that this thing is nice in the commutative case. If I assume that if two coordinates of a single point commute, then two coordinates of two different points will commute as well, and everything is covariant. In the non-commutative case, this is not the case. I can have one coordinate that closes the, say, k-Minkowski algebra, another that closes its own k-Minkowski algebra, and they are comodule. But if they commute with each other, they can't be a comodule. The commutators won't be preserved. Okay? So this breaks Poincaré invariance. Okay? We need to build what is called a braided tensor product. It's easy to build it for these three models. For theta, I think Paolo found it first, I don't know. It's just that each pair of coordinates, even if they're not the same coordinate, their commutator gives you a theta matrix. For zeta, I think I put it out for the first time in one of these papers I mentioned. And for kappa, in a paper with Fedele Lizzi, we show that this is a comodule. However, these commutation relations, which are still, you see, linear in the coordinates of the 2 points, they have a problem. They do not satisfy the Jacobi identities unless the V vector, let's call it vector, is lightlike. Okay, of the 3 kappa-like models, only the lightlike one admits, you know, an associative algebra of endpoints that is covariant under Poincaré transformations. Okay, so this is an issue. We will focus from now on, when I talk about kappa, I will only focus on the what I call kappa lightlike. Okay? All right. Differential calculus. The differential of one coordinate is just 2 coordinates that are very close to each other. Okay? If I introduce these guys, the difference between 2 different coordinates in the braided tensor product algebra, this guy is a module for the algebra of 1 point. Okay? Their commutator with 1 point is always proportional to delta x, the difference between coordinates. This is a differential calculus. You can just replace delta x with dx, and this is a covariant differential calculus, which has all the nice properties and satisfies the Jacobi relations. So if I have the braided tensor product, I have a 4-dimensional differential calculus, okay? Also for kappa, the kappa lightlike model admits a 4-dimensional differential calculus, even though the timelike doesn't. Okay, finally, I would like to remark that these three models can be written very compactly with an r-matrix. This is really a 5-dimensional representation of an r-matrix. So it's just large A is an index that goes from 0 to 4. It's a 5-dimensional index in the standard 5-dimensional representation of the Poincaré group. Okay, and big T are Poincaré matrices. So their space-time components are the Lorentz transformations, and the mu4 components are the translations. The 4 mu components are 0, and 4 is 1. This is standard representation of the Poincaré group. I can write all of the commutation relations from before by choosing an appropriate R matrix, and I will get the group commutation relations, the homogeneous space commutation relations, where XA is the 4 coordinates of space-time and 1 for the 4th coordinate. Then I get the braided tensor product structure, just the same, just taking 2 different points here, and I have the differential calculus as well, where of course dx large A is dx mu and 0 because the differential of 1 should be 0. Okay, so this is a very compact way of expressing everything I showed you so far. You just need to find the right R matrix. Okay, not talking about a universal R matrix so far. It's just a 5-dimensional representation thereof. Okay, so it's much simpler. All of the above is covariant under, the action of the Poincaré group on X and on XA and the differential calculus, as well as under the coproduct of the group, which again has to do with composing Poincaré transformations. Okay, nice. Okay, I got this in those papers. I can write by assuming that my commutation relations derive from a form, take a form like this, and assuming something about the commutators, that certain, so on the right-hand side, I can only have terms that are linear or quadratic in lambda and A, because everything is quadratic, but one of the components of the T matrix is 1, okay? So I can have A lambda, 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 and 1, and lambda A. Some of these are excluded by a set of assumptions I make, which are physical in origin. For example, some of these terms would require an inverse length scale in order to make sense dimensionally. And when this goes to 0, because I'm imagining it's some Planck scale, this diverges, that is telling you that the large scale limit is not very good. So I exclude those. But with all of this, I can express everything I showed you in these terms. Commutation relations between the A's that are a function of the lambdas times this antisymmetric matrix, which reminds us of the theta Moyal matrix. Oop. And then I have a Lie algebra-like object. The lambdas commute, and lambda with A gives me a sort of action of A, of the translations on the Lorentz group, like vector fields that act on the Lorentz group, okay? F are structure constants, quote unquote, because they're not antisymmetric in these alpha and beta indices, okay? So they're not, in fact, their antisymmetric part here plays the role of structure constants for this Lie algebra-like term. They are 64 parameters. And theta are 6 because it's antisymmetric. The quantum Minkowski space is this. That's wrong. The quantum Minkowski space is this plus a term just like this, okay, with X in place of A. This is a typo. The braided tensor product structure is this. C, I didn't write it, but C is the antisymmetric part of F, okay? So everything is in terms of 64 plus 6 parameters, 70 parameters. This is not all. I need to apply some conditions, namely that these are satisfied and are preserved by the commutators, so that the commutator of this equation essentially with everything is 0. And I have to apply the Jacobi identities, of course, in order to have an associative algebra. Well, here it is. The Jacobi identities for C are satisfied. So C are the structure constants for a normal Lie algebra. Theta is a 2 cocycle for that algebra. So I can choose my Lie algebra, whatever, and then I can see what cocycles are admitted on that Lie algebra. Okay, so that is calculated after knowing what C is. Okay, and then there are 2 constraints on F. This, which is quadratic, and this, which is linear. These 2 constraints are very simple. The linear constraint just tells you that if you introduce these 4 matrices, K mu, whose components are given by F alpha mu beta, these are Lorentz algebra matrices. Because the relation just tells you that if you lift the 2 indices of the K mu matrix, they are antisymmetric in those 2 indices. Okay, so they're Lorentz antisymmetric. They're Lorentz matrices. Simple. The second constraint is beautiful. It tells you that those K mu matrices close a Lie algebra that is isomorphic to the Lie algebra of the coordinates, essentially. Okay, so I need 4 Lorentz matrices which close the same Lie algebra as the coordinates of space-time, and I get a model. Okay, cool. How many models do I get? Do I only get those 3 that I started from? No, I get 16. If I write all of this in terms of the R matrix, it turns out that I can write it, because it's a 5-dimensional representation, I can write it in terms of a nilpotent small R matrix, so something that whose square is 0. And so there's an expansion in powers of the deformation parameter terminates at first order, and I get an R matrix that takes this form. The theta term times P wedge P. This is what appears in the twist for theta Poincaré, for example, or in its R matrix. And then a term that involves that K matrix that involves the structure constants F from before. Wedge P. P is just a 5D representation of translations in the Poincaré group, and K is this linear combination of Lorentz generators, okay, in the Poincaré algebra. The quantum Yang-Baxter equation, which is cubic, because R is nilpotent, turns into the classical Yang-Baxter equation. So I just need triangular R matrices in order to classify all my models. And this was done for me by Zakrzewski, did I pronounce it right? In 1997, or 6 even. Yeah, because it was on the archive in 96. There are 2 typos in this paper which were fixed by Tolstoy in 2007. There are 16 triangular R matrices, and then there are other 6 that satisfy the modified Yang-Baxter equation, classical Yang-Baxter equation, which I'm not interested in here. And I like to pack them into 11 models because there are the 3 kappa. Kappa is only 1. There are the 3 zeta Minkowski, which are really 1 with the same, if you use 1 vector to indicate them all. And there are 3 classes of automorphisms of the Poincaré group, which correspond to Moyal, because that matrix theta mu nu separates in 3 that are inequivalent under automorphism. So I like to pack them all together as a Moyal non-commutativity. Okay, so I have these 11 classes of models. They have more than 1 parameter usually, real parameters. And these are the most vanilla ones, the black ones. Then there are 4 that are non-unimodular, because the Lie algebra of coordinates is not unimodular. This will be important. And there's 2 that admit no cocycle, so no theta term, okay, no Moyal type no contribution to the commutators. And one of them is the kappa lightlike I was talking about, is here. All the other ones don't have letters, so feel free to use the rest of the Greek alphabet, which has more than enough room for all of them. Okay. And nicely, the kappa model is not just kappa lightlike. There is a 1 parameter generalization of that model. It's here as this parameter. I just wanted to show you. Okay. One thing. I said, just like Maria, I think that I understand quantum homogeneous space as comodular algebras. Okay, this is not the strongest requirement I can make. There is a stronger one called quantum embeddable spaces. These are when the coordinates can just be written as the translation generators, essentially, of the corresponding Poincaré group. So here, when these A's close the same algebra as the X's, it means that theta is 0. Then I have a quantum embeddable space, because it's literally a sub-manifold of the group manifold it belongs to. And so I have this only when the cocycle is set to 0. Okay, you find here the details of these constructions. Also, when theta is 0, I have Majid's bicross product construction. So all the T-Minkowski and T Poincaré models I showed you are a sort of a generalization of the bicross product construction. Okay. All right. How much time do I have?
You have almost 20 minutes.
All right. Nice.
That's including for discussion.
Sure. Okay. I want to show you how so now we have a nice playground of models to play with. And I haven't mentioned it, but I think that these are pretty much the simplest non-commutative spacetimes that admit Poincaré invariants that I can imagine. Maybe there are simpler ones, but really, Moyal, not by chance, is one of them. How do you work with them to build field theory and maybe quantum field theory? Okay, Maria showed you already many techniques. I want to show you the particular point of view I have, so the way I do calculations, essentially. This is the commutators of the coordinates, and they are a Lie algebra. If theta is 0, if theta is non-zero, it's just a central extension of a B algebra, okay, of a Lie algebra. Okay, really all this main structure is in here, in the Lie algebra part. The rest is just a sort of twist added on top of it, okay? There is a very nice paper by Fedele Lizzi with other people who introduced the concept of generalized while systems, which work for exactly this type of Lie algebras, okay, where you have a central extended general Lie algebra. And this is what I will use to work, to define non-commutative functions, essentially, functions of my non-commutative space, and Fourier transform, and all of that I need in order to do field theory. We start with ordered plane waves. This will be a base of non-commutative functions. They are formal infinite power series, and this is just a standard exponential formula with a frequency or momentum k, which is just a real, 4 real numbers. And there is an ordering symbol here. This you can see as a while map if you want, something that prescribes in which order I put the coordinates. They can even be symmetrized or while ordered. I will get different formal polynomial, formal series here if I choose different orderings. My claim is that we should be careful in trying to do physics in a way that doesn't depend on this choice, because this is just a representation of a space of function that is there independently of this choice, okay? All right, so choose one ordering. The product of plane waves, there are many techniques to calculate this. I have even a universal representation from my x coordinates that allows me to do this in Mathematica in 1 minute. What I get is a phase that is Moyal-like, okay, and is linear in theta. And then I get this guy here, a composition law for momenta. Then the involution gives me an antipode map, really. And the calculating this in 0 gives me the unit. Therefore, I have a co-unit. Delta, S, and epsilon close an Hopf algebra. This is the Hopf algebra of momenta, if you want, okay? And it's just the functions on the Lie group dual to the Lie algebra of coordinates, except that when theta is non-zero, this algebra of function is twisted by theta. This is the whole story.
10 plus 5.
10 plus 5, thank you. If I change my ordering, so I change, I don't know, I put x0 to the right first, and I get E, and x0 to the left here, and I get F, another ordered plane wave. Well, I can change my, I can translate, I can show that the old plane wave can be expressed in terms of the new plane wave. How? Well, there is a phase, and there is a possibly nonlinear coordinate change in momentum space. We know this is a Lie group. If I change my factorization of the Lie group, I get a different coordinate system on the Lie group. This is what it is, nothing more. So this is a diffeomorphism of momentum space. If I want order independence, I need to make sure I have a diffeomorphism invariance in momentum space at all stages. Otherwise, I will be introducing some arbitrariness in my description. But it's possible to do it. I have a Lie group, so I have left and right invariant r-measures. They are related by the modular function. When I still have time, right? Yes. It's okay. The modular function is one when the group is unimodular, precisely for this reason, and it introduces complications because we have one left and one right invariant measures which do not coincide. Okay, now I have a notion of non-commutative Fourier theory. I take a general element of the universal enveloping algebra of that Lie algebra of coordinates. These are functions for me. I write it, I expand it like this, with a left Fourier transform or a right Fourier transform. And then I say, I'm only interested in the functions that whose non-commutative Fourier transform is like Schwartz or some other space of functions that I might be interested in, okay? This way I can do field theory. The left and right Fourier transform, of course, coincide only in the unimodular case. Otherwise, they're related by this famous modular function. And ordering changes, as we said, they reshuffle the labels of plane waves in a nonlinear wave. They are associated to the pullback of diffeomorphisms on these Fourier transform functions. Okay? I can also work with star products. It's an equivalent description. And actually, since recently, very recently, we have a paper by the group of Jean-Christophe Bollet showing the star product for all these models, except one for reasons unknown to me so far. But anyways, I can work with Fourier transforms. I can introduce the integral in the really most straightforward way. It's this linear map on the algebra that gives me the delta function distribution when applied on a plane wave. Turns out that this acts on the same way on all plane waves because it calculates it at the zero momentum. And so they're all equivalent in that point. I can prove it. And so the integral is just calculating the Fourier transform at the origin, nothing more. This is invariant under the coaction of the T Poincaré group, okay? In this sense, that if I act with the integral on the right-hand side of the tensor product of a Poincaré transform function, I eliminate all dependence on translations and Lorentz matrices, okay? If the model is non-unimodular, the integral is not cyclic, well known. If I swap functions, I get this modular function, which is a function of momentum and therefore acts like a derivative operator on the functions. Okay, differential calculus, I showed you most of it, but the whole theory of differential geometry on non-commutative spaces is well known since the end of the 80s. You just read Voronovich's seminal paper. And I can write the action of the differential operator, just the one that Maria showed, the one that satisfies Leibniz, on arbitrary functions. And it depends on this operator. which is a function of momentum space, okay? I have a closed formula for xi for all the T Poincaré models, which is good looking because now it looks like I can do field theory in the whole generality in any of these models. And it turns out that it is Lorentz covariant. That is, it transforms linearly under Lorentz transformations. The general momenta, the k, for example, in any coordinates on momentum space will not transform linearly. The action of Lorentz transformations can be shown to arise from the coaction of the Poincaré group, and it's complicated in general. But since the differential calculus is covariant, then this xi is the one coordinate system in momentum space that transforms linearly, okay? I can also prove that in all models, if I use xi as momentum space coordinates, the left invariant measure is just flat, trivial. So momentum space is flat. The left invariant metric is flat in all these models, okay? K-Minkowski time-like, no, it's de Sitter, all right? So this is probably what's behind the simplicity of all these models. We have a flat momentum space, okay? All right. With this, we can define the exterior algebra. It's just what Maria showed, so I don't need to delve into too much details. Just know that the basis for one forms close a completely trivial and undeformed algebra. They're anti-commute in the standard way. I can introduce the Hodge star, just the one that Maria showed, left and right linear and all of that. And Lie derivatives, inner derivatives, I can do all of these things. I can define Klein-Gordon and Dirac, free Klein-Gordon and Dirac fields. There's only an ordering ambiguity when the model is not unimodular. So there are two ways to write the action. I can also, I didn't write it here, but okay. The space of classical solutions is the same regardless, or at least the bulk of it, regardless of the ordering choice for plane waves I choose at the beginning. So this is what I was talking about in the case of the classical theory. I can also define a notion of Nader theorem, because I can associate to the symmetries, both space-time symmetries or gauge, three form, which is closed only on shell, on the solutions of the equations of motion. So this is nice. Gauge theories, Maria said it, they're problematic because in non-unimodular models because of the cyclicity. I know at least 5 different ways that have been proposed to solve this, in particular for kappa time-like. So, but they all complicate the theory. You won't have a simple action like this in most of these approaches. All right, this is for the classical theory. How much time do we have? 1 minute. Okay, just in 1 minute, I want to show you baby steps towards quantum theory. It is to use the braided tensor product algebra. One very interesting property of this algebra is that the difference between coordinates, okay, A, B, C, D are 4 different coordinates. When you take their difference, this object is translation invariant, no, obviously. They close a commutative subalgebra. So endpoint functions of quantum field theory should be translation invariant, should be Poincaré invariant. They will belong to a commutative subalgebra. My proposal is modest proposal. Let's just interpret these as standard endpoint functions, as I would on commutative spacetime. They are commutative functions, after all. Okay. To do that, I want to show you this other interesting result. When I take translation invariant products of plane waves calculated at different points, I can prove that they are always take this form. This commutative difference of coordinates times the coordinates of momentum space that transform linearly under Lorentz transformations, independently on the initial ordering, okay? Of course, the expression of xi as a function of the initial momentum will vary depending on the ordering. However, if I integrate this in something like a Pauli-Jordan function, for example, the integral will, and the measure can always be written in the xi-coordinate independently on the initial coordinates. So it always reduces to the standard formula, the non-deformed Minkowski expression. What we're doing is, all of this works well only in the unimodular case. The non-unimodular case introduces significant challenges, in particular because really I have to consider other types of plane waves and a disconnected component of a momentum space. This is just a sketchy description of what goes on. But anyways, my proposal for free field theory would be to do something like that. Assume the standard assumptions about microcausality, Lorentz and Poincaré invariance, and so on, and define a quantization like this. Well, for the unimodular models, I get something that, for all these models, only the ones that are unimodular, I get something like equals all result for T-Minkowski. That if I have both deformed statistics, that is, the creation and annihilation operators have a deformed algebra, and non-commutative coordinates, then I can have Lorentz invariant endpoint functions, but they are trivial. They're non-deformed. They're the standard. And here I leave it because the price to pay to have non-triviality, all the ways that I looked into it so far, is to have Lorentz breaking. For example, at the level of 4-point functions and so on. So this is very open. I also would like you guys' opinion on this matter. But this is as far as I got. Thank you.
Hello. So all this is very nice, but it is mainly kinematical part. You mentioned several approaches how to construct gauge theories on K-Minkowski space. What about Zeta-Minkowski that you also mentioned here? Do you know some work in this direction?
Yeah, Jean-Christophe worked on that. I think we have some of his collaborators here that worked on these papers. Okay, I don't want to. Maybe I can't make justice to the community, but this is the one that I can think of. And but rho is unimodular, so this is cyclic, and so I think here I have no problem. I can just do at least a abelian gauge theory. Of course, you need to have a Maxwell tensor that has a Maxwell 2 form that has the commutator between the form fields, the gauge fields, because it's non-commutative. But we don't have this problem there. Actually, well, what are the non-unimodular models? Just 4. There's only 4 of them. So theta, of course, there's a lot of literature on gauge theory on Moyal. And then there's all of this in which it should work right away, and so on. If you're asking in general about interacting theories, well, that's another matter. I could define a path integral in the most natural way, but I'm seeing that it's very easy to end up with something non-Lorentz covariant. So it's under investigation.
One short comment regarding taking the difference of two space-time points as generating a commutative algebra. I think you should have mentioned also our paper, my paper with Julius West.
Did I not?
I mean, it was a basic result.
Yes. Apologies. So Gaetano and Julius West
it
as
allowed
well.
also to develop, start developing a perturbation theory. So it's important. Which one of these, for which one of these deformed zeta Poincaré, there is, I mean, it's known also a twist, a trivial twist? Do you know?
Twist. They are all twists.
Yeah, but it's known.
There is a twist, there is an r-matrix, a universal r-matrix for all of them. Tolstoy classified them, and they can all be written in terms of a twist.
Explicit twist.
Yeah. It's complicated because it's not an abelian twist. So you have products of exponentials of p, which p is p, tensor m, stuff like that. So there are three papers that I should have mentioned here regarding the coordinate difference. There's Gaetano's paper, and also Paolo, I think, has something to do with that observation of the braided tensor product structure. So apologies for getting your reference. Yes?
I have two comments. First one is that we clearly have lots of models, so we should try to cut them down. And one possibility is to see if there is some sort of causality, non-commutative causality, so the role of time. I don't really know. Some of them are not causal, but they are sort of asymptotically causal. So this could be a criterion to reduce them. So this is just a comment. Second comment is that I was checking the Hiragana Japanese alphabet has 48 symbols. Oh. So probably we should go into that direction, because then we can, with the 19 missing Greek and the 48, we can probably put one letter for everyone.
We can put more out, yes. Another comment regarding that asymptotic causality is also that here I think in all these models we have a notion of asymptotic commutativity, because it's linear in the coordinates. So very far from the origin, the angular coordinates will stop being, they will be suppressed, their commutativity. So maybe it's a universal feature, what you said about causality, I don't know.
Maybe I just wanted to ask, your construction looked very much like you could easily extend it to de Sitter, right? Because you were using Wigner
easy.
In a new,
well,
do you
sacrificing some
do you get a simplification or an additional complication?
Complication, because I will have here. This can be done with de Sitter. I just have to change the algebraic relations between the t's. Yes, but then this is for the de Sitter. I don't know how much work there is on the r-matrices on that.
We should go to lunch.
All right. Thank you.